All right, so I'm going over learning objective number 2, so I just need to describe to you the neuromuscular junction, the role of calcium first. The first step we're going to have is an action potential traveling down the axon in the neuromuscular junction. This is going to lead to a depolarization, leading to the opening of voltage-gated calcium channels, leading to influx of calcium at the terminal bouton. This calcium influx is going to be sensed by synaptotagmin, which is a protein found on the surface of the vesicles, and that's going to cause fusion of the snare complex, contraction of the snare complex, leading to release of acetylcholine into the neuromuscular cleft. That acetylcholine is going to travel by means of acetylcholine receptors located at the peaks of the invaginations on the muscular side of the tissue, leading to an action potential moving downward into the clefts where voltage-gated sodium channels are going to lead to potentiation of the action potential, which will inevitably lead to muscular contraction. One of the reasons why calcium is so important is because it causes fusion of the vesicles by means of synaptotagmin in the snare complex. It can be found on the extracellular side as well as intracellular in reservoirs of calcium found in mitochondrial concentrations at the terminal bouton. Now, mitochondria can be found in the terminal bouton, A, to serve as reservoirs of calcium, and B, because we need a lot of ATP to load our vesicles and cause fusion with the membrane. Particularly with acetylcholine loading, there's a pump here that causes acidification of the channels, and it's an ATP-powered pump. So it makes sense that we're producing lots of ATP at the terminal bouton to load up our vesicles and cause eventual fusion with the membrane. The learning objective was to describe facilitation as well as potentiation. To do that, we can make a little graph. On the y-axis, we're going to have quanta, which is the acetylcholine vesicles that are fusing. And we also have time. Let's say, for example, we're eliciting a stimulus over a small time period. We're initially going to have a very low quanta level because there's no action. Sorry, I did that in black. Let's see. There's going to be no action potential because there's no stimulus, and therefore you're going to get very low levels of fusion and acetylcholine release because there's no calcium influx causing that fusion. However, once the stimulus starts, you're going to get a very quick increase and a slow decrease down to the point where you might even have a little bit of depression. So this peak is called facilitation. And this is just referring to the fact that once we've received that stimulus and depolarization, the calcium availability is going to slowly increase extracellularly at the terminal bouton. And all this calcium we have outside of the neuromuscular junction can now elicit fusion of the vesicles containing the acetylcholine. And so it's facilitated because of the increased amounts of calcium. As the stimulus continues onward, it gets easier and easier and easier because the calcium concentration is already there, so we can release all the vesicles that we have. But it's slowly going to decrease. Say if you have a stimulus over 10 seconds, we might use up all the acetylcholine to the point where it could even be depressed below the initial value that we saw before the stimulus even occurred. Now the next step of this is we're going to get a slow increase, or a pretty quick increase, but a little slow die off. And this second peak here is potentiation. Now, even though the stimulus is stopped, we have lots of extracellular calcium. And while we might not have a stimulus, we might get calcium influx in the terminal bouton. In addition, at this point in time, the mitochondria are releasing their calcium stores, and that could lead to further sensing from synaptotagmin, which is causing the snare complex to release the vesicles, and we have potentiated the release of acetylcholine because of the calcium concentration.